Okay, should be recording. Take it away.
Can you guys see my screen?
Yes.
All right,
Yep.
sweet. Okay, welcome to Group 12, the Productive Pipetters final design presentation. We really appreciate you guys taking the time to come here and see what we've been working on all semester. So this is our pipetter. It consists of 6 major parts or subassemblies. We have the 3D printed drive nut that is used to move the plunger up and down inside the nozzle. We've got our motor, which we used a NEMA 17 stepper motor in order to drive the nut up and down with the plunger. The plunger and the nozzle are both made out of aluminum in order to make them cheap and easy to manufacture. The top of the plunger, which interfaces with the drive nut, is designed to be a press fit so that there are no fasteners required to keep it in place. The end of the nozzle is tapered to provide a press fit that will keep an airtight seal with the pipette tips. And it's also large enough to carry a volume of over 5,000 microliters. And this allows us to have the extra length for movement to remove the pipette tips. And the tip dispenser is assembled as 2 separate parts and only needs to move at the end of the drive nut's travel after all the fluid has been dispensed. And the dispenser resets to its original position by using a spring at the bottom of the housing. And our housing is completely 3D printed and restricts the rotational motion of the drive nut so that it can only move in the vertical directions. We also have a limit switch, which isn't pictured in this, this view, over where there's 2, it mounts onto the 2 holes on the side of the housing. So here you can see exactly how each part fits together. Our design only uses 1 fastener to hold the tip dispenser together and 4 to secure the motor to the housing, and then another 4 to secure the tool housing to our pipetter. And this makes it easy and quick to assemble and disassemble. And this video shows the full operational motion that our pipetter goes through during a 1 cycle, taking in fluid and dispensing fluid. So as you can see, the drive nut comes up and down to use the plunger to pull fluid in and out. And when it's ready to dispense a tip, pushes down a little bit further onto the tip dispenser, which will knock off the pipette tip. And then as it rises again, the tip dispenser will reset to its original position through a spring that isn't in the assembly right now, but it would be at the top part of the top dispenser piece. So here we have the total cost breakdown of our pipetter. So the tool plate that controls the up and down motion of the pipetter costs $18.98. Our limit switch is around $2.95. Then we have 9 M3 screws, which total to $306. Our nozzle is a made from 5/8 inch aluminum round stock, and that costs us $463. Our plungers uses 1/2 inch aluminum round stock, and that's $218. Our NEMA 17 motor was $28.99, and all of our 3D printed parts together using PETG filament, which is priced at $21.99 per 2 kilograms for a spool, costs $415. And that totals at $64.94, which comes in below our budget of $100.
Our system is capable of picking up a maximum volume of 5,000 microliters along with the minimum 500 microliters. As stated before, we use a 3D printed drive nut to translate the rotational motion of the NEMA 17 motor into linear movement along the Z-axis, as you can see in the picture on the slide. Since our mechanism uses a plunger attached to the drive nut, and that drive nut rests on a lead screw, we were able to calculate the tolerance of the fluid extracted based on the tolerance of that lead screw. So the lead screw had a tolerance of 0.04 millimeters. And also the tube in which the plunger travels has a diameter of 11 millimeters. So by knowing our lead tolerance, which is in the Z direction and the cross-sectional area, we found that our tolerance based off of the lead ended up being plus or minus 3.8 microliters. Our total tolerance will be discussed later in the presentation. In order to ensure that the dispensed liquid did not have any aerosols, we designed the assembly to have a Reynolds number under 2,300 for the maximum liquid dispensing rate of 2,500 microliters per second. The motor speed necessary to displace at that rate was found to be 198 revolutions per minute. This was done by finding the necessary plunger displacement speed to achieve that max flow rate. Since a disposable pipette tip will be added to the nozzle circled in red, the Reynolds number calculation used the outlet area of the disposable tip, which was 1.6 millimeters in diameter, and its resulting exit velocity to get a Reynolds number of 2,020.
Gabriel, you're muted.
I knew that, thank you. So over the course of the semester, we made 4 significant changes to our design. Some were through testing and some were accidental, but we're able to thoroughly improve the design over the course of the semester. So initially we had 3 columns in our tip dispenser, but as you can see in the picture, they were very thin. And what we experienced during the course of the semester is that as we would print them, they would be too thin for a taped hole with threads. We then decided to change this and we decided to use only 1 column instead, and we made it thicker, as you can also see in the picture. And this allowed us to put some threads in the hole. Next, we have the nozzle taper. So initially, this was a little too steep, and because of this, it wouldn't press fit with the tips very well, and this would cause it to not connect very well. So we had to increase the bottom diameter for a better seal and a better connection between the tips and the nozzle. Furthermore, next, we also had to make changes in the drive nut. So as you can see, well, as we mentioned, we ended up 3D printing the threads, and this worked very well. We also decided to change the size of the hole for the lead screw and the plunger piston so that we could have a better fit. And we decided to use a step in our drive nut to push off the tip dispenser. And lastly, one important change that we made as well is adding fillets at the top of the housing for support with cracking so that it would stop it from breaking. And speaking of housing, Alex is gonna talk more about that next.
When we began to analyze where mechanical failure would occur in our assembly, we realized that the housing unit had the highest concern. More specifically, our concern for failure was that it would fail at the edge of the housing. If failure was going to occur, it would be from the forces caused by the motor. In order to mitigate failure on the housing, we calculated the forces done by the motor and assessed the geometry of the housing and analyzed where the highest stress concentration would occur. The lowest area of the housing is in the middle, and the highest stress concentration occurs where the middle connects to the top and bottom plates. From the stepper motor's datasheet, we found that the maximum thrust done by the motor is 12.5 kilograms. Assuming that the force of gravity is a constant 9.81 meters per second squared, the total force done by the motor is 122.63 newtons. Since this total force is a distributed force, we created a shear force diagram for the distributed force across the length of the bottom of the housing. From the shear force diagram, we can see that the highest force along the length of the bottom of the housing is 61.32 newtons. This is the force that we use to analyze the stress concentration. We used SolidWorks to find out that the area of this section of the housing is 165.03 millimeters squared. Pressure is calculated by dividing the force by the area. Using this formula, we found that the highest stress was 0.372 megapascals. After figuring out the maximum stress on the housing, we needed to confirm that our housing material could withstand the stress. Our housing unit was 3D printed with PETG filament. Online studies placed the yield stress of PETG between 47.9 and 52.9 megapascals. Another study said that the disparity between the yield stress values for printed plastics and solid blocks varies by up to 33%. We took these two studies into account and calculated that the lowest yield stress of PETG would be around 30 megapascals. These calculations show that our housing will not fail by a large margin. We also physically tested this by sending the drive nut to the bottom of the housing to observe if any failure would occur. After doing this, the drive nut was stalled at the bottom of the housing without any failure occurring. It must be noted that our analysis consisted of simplifications in order to perform these preliminary failure calculations. Some of these simplifications include assuming an evenly distributed force by the motor onto the drive nut and modeling the bottom of the plate of the housing as a pinned beam.
As noted by Alexis, the biggest concern for failure was the housing, and particularly where the center meets the edges, or rather where the middle meets the edges. We never had any problems with the housing during actual testing, which was fantastic, but we actually did have one time where it broke during an assembly. So when we added the fillets, we never had this problem again, which was fantastic. Some of our validation data included testing 5 different trials per volume at 5 different volumes to get a calibration curve, as seen below. The equation from that curve was then used to get a specified volume within 10 microliters, which was our goal, or in our case, 10 milligrams of water. We made the assumption that 1 milligram of water is equal to 1 microliter at a standard density. In order to get these volumes, we used a scale rated to 0.1 microliters accuracy in order to do the testing with water at room temperature in our laboratory. When we tested the design for volume, we found that it had a calibration curve roughly close to what our calculations told us it should be, and it has small offset of about 15 microliters. We assume that this offset is primarily due to the fact that the drive nut has to rotate slightly within the housing before it hits the walls and is forced to translate linear or up and down. This change in calibration constant likely results from the fact that the inside of the nozzle was slightly wider than our nominal dimension, and this is accounted for in our error calculations. Most of our trials did result in an error less than the 3.8 microliters that Jiv calculated earlier, including our recorded test, in which we were only off by 3.5 microliters. Although there were a couple of trials where our errors were slightly outside the mathematical range we calculated of 3.8 microliters, ranging to about 3.9 or 4.0 microliters. We assume that this is caused by 2 major factors that we didn't account for. One of which is that the piston is probably not completely vertically aligned, and there's some small 1 or 2 degree offset that could potentially change the exact range that it pulls. The other is that there's some potential for mechanical movement within the system while it's operating that could cause some small bits of the water to either not be picked up or the movement to not be completely linear. These issues still kept us well below the 10 microliter tolerance, so we didn't feel the need to account for them later, but if we were to update the calculated tolerance we made, we would probably put it around 4 microliters. This would also be useful if we ever had to make a more precise pipetter later on, in case we wanted to either work with larger volumes or simply increase our accuracy. Anyway, thank you very much for your time. Do you have any questions?
All righty, go ahead and open up
the floor for any questions from the panelists.
Yes, this is Rick Miles at Northrop Grumman. Quick question there on your calibration curve. Are those dots actual your 5 tests? Because it seems extremely straight. That's why I was just curious.
So those 5 dots are the averages of all our tests, but even when we plot them separately, they're very, very close. This was always so close that it was hard to really see the difference. So we only added the average dots.
Okay, thank you.
Can you go back to the animation?
This one or the one before?
This one, I think. So you have that, you call it is it the drive nut?
Right here.
That piece. So it's moving up and down in your, like you said, it's press fit in there.
So the drive nut isn't press fit into the housing, but the plungers press fit into the drive nut.
The drive nut has a slight bit of room on either side, and once it turns, it's forced to stop rotating and translates to linear motion.
So, okay.
Yeah, there's a hole right here that threads onto this lead screw. So as the lead screw turns, it forces the drive nut up and down since the drive nut can't rotate around.
Okay. And so there's like I guess a gap between the nut and the housing.
Yeah, there's a small amount of clearance between the walls of the housing and the sides of the drive nut.
Okay. So then the plunger, I guess, is press fit into the drive nut, right?
Yes.
Okay. Did you look at like that section failing? I mean, if you don't have the proper, I guess, press fit or assembly or contact pressure, did you look at that at all? If it could slide out or over time? Or
we actually tested it with a variety of sizes for the holes. So we used guides in our textbooks to tell us what the size should be, but we did test within a couple of millimeter size differences within those. And we used these for the entire time and it never slid out. It was press fit well enough. So we found that the best was to make it a little bit tighter than the book said, but we did test for that, yes.
While we're talking about the drive nut, this is a 3D printed piece and it's running on what, a steel lead screw?
Yep.
Are you concerned about wear of the threads and how that affects potentially backlash, how that affects your calibration over time?
So there is concern that it could over time fail, but ours is listed to be used without change for about 2 weeks, I believe. So we found that within that period, it doesn't cause a problem. If we were to try to make one that would work longer term, we would probably look into that more, but this seemed sufficient for the time. We also slightly expanded the size radially of that hole, or rather of those threads, to make sure that there wasn't so much interference and that it didn't have so much friction. We think this caused it to move not only much smoother, but it caused less wear over time.
So you're saying that because this thing will last for the 2-week span of an experiment, that it should be okay?
Well, that's the customer needs requirement, says that it should last for 2 weeks. We designed it to meet those customer requirements.
I would suggest that maybe that's a misunderstanding of the customer needs, right? I mean, I don't think anybody would anticipate having to replace a component of their test rig every 2-week experiment, something like this. So I don't think that's the right measure for you guys to be using there.
Okay,
and
thank you.
kind of on a similar note, if it is something that needs to be replaced with any sort of frequency, a press fit may not be the right way to hold things together, right? I mean, that's not easy to disassemble, and something like a set screw might be more appropriate.
Yes, thank you. We'll look into that.
Can I ask? I asked the last team, and I think there's maybe a little confusion about really the answer on this. And Dr. Traum put something in chat. Is this like a one-off build, or are you expecting to have this as commercial production in the hundreds or thousands of units?
I'm not sure exactly if this is supposed to be a commercial like product.
My understanding of the product was that it was going to be given to one of the team members at the university to be used in their microbioreactors. So I guess it's not necessarily a commercial product that's going to be sold in a large scale, at least for now.
Okay, you may want to check the chat window. So under the assumption that this is a product that gets commercialized, how does that impact your design and with regard to the materials and manufacturing processes that you're speccing out?
All of these parts are pretty, I feel like wouldn't be hard to mass produce, since the majority of them are 3D printed or easily like machined, because the only two machined parts that we have here are the plunger and the nozzle, and both of those are done on the lathe with and aren't overly complex.
If we were to look into longer lasting materials, we would probably switch from the PETG and 3D printed materials long term. However, this project required very quick turnaround for a lot of our pieces and very quick turnaround for the ability to test. So 3D printers were the best option for us then, but we would probably look into some other materials than 3D printed materials for mass manufacturing.
Do you expect that would change the design significantly?
I don't think significantly. I think the shapes are mostly, outside of the outside housing, relatively simple. That part would probably have to go through some changes, but the large majority of the components are relatively simplified as they are. So I don't think we would need a lot of design changes to most of the parts.
Okay.
When you were doing the shear diagram, what location were you looking at? It's hard to tell. I mean, it would help to have a picture there, like a cross section or diagram or force diagram, maybe.
Correct me if I'm wrong, Evan or Alexis, but I think we were talking about this portion down here at the base of the housing.
Yes, that's correct. It's at the base of the housing where the center connects to the bottom plate.
So the area that you mentioned was, what was that?
It was 165 millimeters squared.
That's the cross-sectional area of the housing there?
That is the, yeah, of that for that section.
It's where the bottom meets the middle, where we added fillets. It would be that section.
I'm going to go ahead and say I'm not sure I follow exactly where the shear diagram came from, and I'm a guy who loves a shear diagram. Don't get me wrong, and I certainly appreciate that you guys were doing hand calcs and stuff rather than a FEM in this. But I guess I'm not real clear on where that shear diagram's coming from.
So maybe I can try and explain again. Do you see the bottom plate where the bottom plate of the housing, the outer housing?
Mm-hmm.
And then if you see the middle section where the drive nut is connected inside the housing, that section where the bottom plate connects to the outer middle of the housing, that's where we did our calculation.
Yeah, so it's if the drive nut's forced all the way down to the bottom, the pressure it's putting on this bottom section of the housing right here, that's I believe where our shear force diagram is coming from. That was just if we accidentally were to drive the nut all the way to the bottom further than it was supposed to go, would it fail or would the drive nut stall? And in practice, the drive nut stalls, and our calculations show that the PETG material shouldn't fail.
Yeah, I guess I'm having trouble visualizing, excuse me, where the shear is, and where the shear diagram is coming from there. I will say that I, it's good to consider the, a failure mode as sort of your bounding load case. And so I definitely appreciate that you were thinking along those lines.
Thank you.
Yeah, I think it would help definitely to have a cross-section view or something.
Thank you. We'll definitely consider that for the future.
Yeah, include the cross section when you guys put it in your final report, when you actually write it up.
Okay, yeah.
So, yeah, on that note, we're going to go ahead and wrap up here. So thank you guys for the presentation. Job well done. Congrats, you're free. And we'll go ahead. I noticed about 5 minutes ago, the next group starting to pile in. So we will free. Yeah, free. I noticed the next group starting to pile in. So we'll go ahead and switch over and get the next group keyed up here.
All right.
So
Thank
thank
you,
you
guys.
guys again.
Thank
Congrats.
you.
Thank you so much.
Thank you. Have a good
Thank
one.
you.